My name is Grace, and the other leader today will be Kevin. You want to introduce yourself, Kevin?
Right, hello guys. I think I'm having a little reverberation, but I am Kevin. I'll be doing the second half of the exam review, and we're planning for the review to last at most until about 10:30. So, as how the exam reviews are going to go for this semester, we're going to start off with a large presentation. It's kind of like an overview of the concepts you guys have learned in this class so far for the exam, and then after that we're going to break out into smaller breakout rooms. We have about 8 or 9 leaders on tonight, so it'll be about 8 or 9 rooms, and we'll be doing practice problems in those rooms, so you guys get a little more practice before the exam. So while me and Grace are going to do the presentation, we'll have the other leaders go ahead and answer your questions in the chat. We won't be checking the chat as frequently, but if you do have a question, go ahead and respond or go ahead and ask, and our leaders will be monitoring that and trying to give you feedback as fast as they can. All right, with that all being out of the way, we can go ahead and begin.
Awesome, thanks, Kevin. So, to start out, we're going to be talking about Chapter 13, which is the physical properties of solutions. So, what are solutions? A solution can be defined as a homogeneous mixture of 2 or more substances, and solutions consist of a solvent and a solute. So the solvent is the medium into which solutes are mixed, and that is usually a liquid, and that's going to be the greater amount of the 2 components of your solution. And then the solute is the component that gets dissolved into the solvent, which is in the smaller amount, and this is usually a solid or a gas. So solubility defines the amount or the mass of the solute that can form a saturated solution with a given mass of a solvent at a specific temperature. So the types of saturation which I referred to with the solubility are saturated solutions, unsaturated solutions, and supersaturated solutions. Saturated solutions contain just as much solute as can be dissolved at a given temperature. If you have an unsaturated solution, you've put in some of your solute, but you can dissolve more at the temperature that your solution is at currently. And then if you have a supersaturated solution, this can happen if you make a solution at a higher temperature and then cool it down. But supersaturated solutions have more solute that can actually be stable at a given temperature. So at a higher temperature, you can put in more solute and it'll dissolve, but then when you cool it down, that new solution actually will be supersaturated and have more than it is stable, and so it can easily crystallize and precipitate. So moving on to entropy, it's talking about the making and breaking of bonds as it relates to solutions. So this can be determined by the magnitude of each of the steps of formation when you're creating a solution. So first, in order to dissolve something, dissolute into the solvent, you're going to have to disrupt the solute-solute interactions. So this is an endothermic process because it takes energy to break bonds. So you're going to have to break the bonds between the solute particles before it can dissolve into your solvent. So after you do that, you're going to need to disrupt the solvent-solvent interactions. So that's the interactions between the solvent molecules, whether it be water or another liquid that you're dissolving your solute into. And that's also an endothermic process, so it takes energy to do that as well. And then the third step is the formation of the solute-solvent interactions. So that's after you've broken apart your solute from each other, you've broken apart the molecules of your solvent from each other, and now you're forming the bonds between them to make your homogeneous solution. And this is an exothermic process because when you create bonds, it releases energy. So with all these 3 steps, taking that in mind, if steps 1 and 2, the endothermic processes, are greater in energy than the 3rd step, then the entire process of making your solution is going to be unfavorable because your delta H is going to be greater than 0, and you're going to have to put energy into the process to make it happen. But then if steps 1 and 2 require less energy than step 3, then it is favorable because your delta H is less than 0. And so the entire process is exothermic and it releases energy. So when we talk about intermolecular forces as they relate to solutions, we talk about like dissolves like. So you may have heard this before. It has to do with the intermolecular forces of both the solute and the solvent. So if the solute and the solvent both have similar IMFs, they're more likely to dissolve. So as an example I've shown here, you have water and methanol, which are H2O and CH3OH. They're both polar, and so they'll both dissolve in each other in all proportions. So they're what's called miscible, if they can dissolve in each other in all proportions. But if we had H2O and, say, something that was not polar, that would not be able to dissolve as well because they have very different IMFs. So if you want something to dissolve in a solvent, you want to make sure that it has similar IMFs to that of your solvent. So moving on to concentration units, we have 3 things mainly that we're going to discuss here: molarity, molality, and percent by mass. So molarity is moles of solute over liters of solution. The advantages of using molarity as a concentration unit is that it's easier to measure volume of solution than the mass of the solvent, because you can just put it in a container that has markings on it, and it's pretty easy to tell how much you have there. But the disadvantage of molarity is that it varies with temperature, because temperature can make the volume of solvents change. So this can cause some problems if you're having a changing temperature, but otherwise molarity is a pretty standard concentration unit that you'll use a lot. And then molality, we have moles of solute over kilograms of solvent. So the advantage of using molality is that this is temperature independent. So unlike molarity, it's not going to change if you have a changing temperature, because there's no volume component to this equation. And then finally, we have percent by mass. So this is the mass of solute over the mass of solute plus the mass of solvent, which is the mass of the entire solution. And then to turn it into percent, you'll multiply it by 100, and that will give you the percent in terms of the mass of solute as it regards to the entire mass of the solution. So the advantages of this is that it's temperature independent because there's no volume component, and there's no need to find molar mass. You can simply mass your components that you have involved of your solute and solvent. So now we're going to move on to mole fraction, which is another thing that you will see in regards to figuring out the ratios between the moles of your solute and then the moles of your solution. So this is the ratio of the number of moles of one component. It can be either your solute or your solvent, to the total number of moles in your mixture, which is your solute plus your solvent. This again is temperature independent because there's no volume component. And then if you were asked to find a mole percent, you would do your mole fraction and multiply it times 100. So on the right side, you can see the formulas for your mole fraction. If you're trying to find the mole fraction of your solute or your solvent, you'll put whatever you're trying to find on the top of the fraction, and then the total moles of the whole solution on the bottom, which will be 1. Because if you add your moles of solute and your moles of solvent together as ratios, they should equal 1 together. So this is similar to the percent by mass, but we're talking about parts per million or billion, because the percent means parts per 100. And so instead of multiplying by 100 when we're finding percent by mass, we're just going to multiply our mass fraction by 10 to the 6th for the parts per million and by 10 to the 9th for parts per billion. So both of these still involve having the mass of solute over the mass of solution like you would for the percent mass, but instead of multiplying by 100 to get a percent, you'll do 10 to the 6th or 10 to the 9th for parts per million and parts per billion respectively. So now we're going to move on to factors affecting solubility. The first factor that we're going to talk about is temperature. This can have varying effects with solids, but it will usually increase the solubility of solids. But oddly enough, it actually decreases the solubility for gases. So this effect depends on whether or not the heat of solution is endo or exothermic. And gases are actually exothermic. So that means heat is a product of this equation. And so since heat is a product, if you increase the temperature, this will shift the equilibrium of your solution equation towards the left side, which is the undissolved solute plus solvent. So you can see in the top right, in an exothermic reaction, heat is a product. And so since you are increasing the temperature, that is creating a product which will shift your equilibrium back towards the reactants. And so that's why increasing the temperature decreases the solubility for gases and other things that are exothermic. And then endothermic has the opposite reaction, which is what most solids are, because it's endothermic. So if you add heat, that is a reactant, which will push your equilibrium to the right and will give you more products, which is your dissolved solute into the solvent. The second factor affecting solubility is pressure, but this only significantly affects the solubility of gases. And the way that it affects the solubility of gases can be defined through Henry's law. So this relates the solubility of a gas by the letter C, and it says that the solubility of a gas is directly proportional to the partial pressure of the gas, signified by the letter P, over the solution. Oh, and then K is Henry's law constant, and that depends on the compound. So you can use Henry's law to relate the solubility of a gas to the partial pressure of the gas, and then usually you'll be given the Henry's law constant unless that's what you're being asked to solve for. So colligative properties are properties that depend only on the number of solute particles in the solution and not the nature of the solute. So that means that it doesn't matter what your solute is, it can be anything. The only part that matters in this case is how many of those particles you have in your solution. So the first colligative property that we're going to talk about that fits this description is vapor pressure lowering. So adding a solute blocks the surface sites for a solvent to escape the vapor phase, lowering the vapor pressure. And if you'll remember, vapor pressure occurs because in liquid and other volatile solvents, you have part of it that is evaporating at all times. And so that is what is described as the vapor pressure. And so if you lower the vapor pressure, that means that not as much of your solvent can evaporate. And so when you add a solute to a solvent, this lowers your vapor pressure, because for a solvent to escape the liquid phase into the vapor phase, it has to be able to reach the surface of the liquid. And if you have solute particles blocking those surface sites at the top of your liquid, then the solvent particles can't escape at the top of the liquid. And so the decrease in vapor pressure is proportional to the mole fraction of the solvent, because if you have more moles of your solute put into your solvent, then it'll have more surface sites blocked, and so the vapor pressure will lower even more because there's not enough space for the solvent to escape. And so now we're going to talk about Raoult's law, which is the quantitative expression of the solution vapor pressure. In Raoult's law, we assume that all of the components are ideal solutions. So all the volatile compounds obey Raoult's law, which on the right you'll see is the observed vapor pressure of the solution, which is P solution, is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So this will take the vapor pressure of the solvent with no solute in it, and then multiply it by the fraction of moles that the solvent still holds after you add the solute. And then that will give you the vapor pressure of your new solution once you've added the solute before and your vapor pressure is lowered. So our second colligative property is boiling point elevation and freezing point depression. These are kind of lumped together because the equations are very similar and the physical properties that we see happening are very similar. So forming a solution causes the range of temperatures where a liquid is observed to increase once you've added a solute. And just as a reminder, the boiling point is the temperature where the vapor pressure equals the atmospheric pressure. And so adding a solute increases this for the reasons that we just described, because it will block the surface sites on the solvent and not allow the solvent particles to escape from the liquid phase at a lower temperature. And so in order for it to boil, then you are going to need to increase the temperature more than you would without a solute in the solvent. And then for the freezing point, the solute inhibits the formation of a lattice during freezing, so the temperature must be lowered, because without the solute, the solvent would be able to make a lattice and form a solid pretty easily. But now that you have those solute particles in there, those are also disrupting the ability of the solvent particles to form that lattice. And so you have to have an even lower temperature to be able to do that. So when we are calculating the freezing point depression and boiling point elevation, we have to remember that the boiling point always increases and the freezing point always decreases when we add it to a solvent. So this means that whatever the change in temperature that you get from your equation, you're always going to add it in the case of boiling point, and you're always going to subtract it in the case of freezing point. So you can see in the bottom right, you have the equations for freezing point depression and boiling point elevation. They look very similar, except for the constant and the change in temperature. Both just have a subscript of F or B for freezing or boiling. That letter K is the molal boiling or freezing point constant, and that's specific to each given substance. And then the molality is represented by M, and then I is the Van Hoff factor. So this describes how much of your solute is going to dissociate once put in a solution. This is 1 for non-electrolytes. And by non-electrolyte, I mean something that is not an ionic compound. It is just all covalent bonds, and so it will not dissociate once put in a solution. And so that's why we say that the Van Hoff factor for a non-electrolyte is 1, because after we add it to the solution, it's still in 1 part. And so the Van Hoff factor really only comes into play if we have a non-electrolyte being added to our solution. And so that will increase in number when we have something ionic or like an acid or something like that that will dissociate in solution. And then you will have your I factor as being greater than 1 because the solute splits into more than 1 part upon being added to the solution. So finally, the third colligative property we're going to talk about is osmotic pressure. This is the pressure required to stop osmosis. And if you'll remember from biology or maybe earlier this semester, osmosis is the movement of water through a semi-permeable membrane. So that means that water is able to go through a membrane, but whatever your solute is not. And so the goal here is to get 2 solutions with the same concentration, which is also the same osmotic pressure, and that's what we call isotonic. So the formula listed here is the formula for osmotic pressure. Pi is the symbol they use to just represent osmotic pressure. It doesn't mean you have to use 3.14 or anything like that. It's just what they use to represent osmotic pressure. And then our other symbols are I, the Van Hoff's factor that we just talked about, that changes based on if your solute is an electrolyte or a non-electrolyte. M is molarity, which we talked about earlier, moles of solute over liters of solution. R is our ideal gas constant, which is equal to 0.08206 liters times ATM over mole times Kelvin. And then because we had Kelvin in that ideal gas constant, our T is temperature in Kelvin. So now just briefly, we're going to talk about colloids. This is just the dispersion of particles of one substance throughout another substance. And the way that this is different from a solution is because you can see down in these pictures on the slide that the light beam is scattered by the dispersed particles that are in the colloid. That doesn't happen in a solution. And so on both of these, the solution on the left, you can't see the particles going through it based on the light bouncing off because it's homogeneous, and so there's nothing for the light to bounce off of. But both of the containers on the right are colloids, and so you can see the light beam going through because there's a bunch of particles in there that are being dispersed, or it's scattering the light. And so colloids can be described as an intermediate between a homogeneous mixture and a heterogeneous mixture. So now I'm going to turn it over to Kevin, and he's going to discuss chapter 14, which is chemical kinetics.
Hi guys, as I understand in your syllabus, you guys are covering about the first half of chapter 14 for chemical kinetics, and we'll go ahead and get started with that. Okay, so chemical kinetics kind of refers to the speed and the rates that a reaction will proceed at. So as you guys might know, that not all reactions will occur at the same speed. So consider like the rusting of iron versus like a conversion of diamond to graphite. So rusting of iron can occur in like a matter of days versus like years for converting diamond to graphite. So because reactions can occur at different speeds, there's also different ways that we can increase that reaction rate. And so here are 4 other ways that you can increase it. So one is by increasing the reactant concentration. So by increasing your reactant concentration, you have more reactant particles that are able to interact with one another to try to produce a product. Second way would be to increase your temperature. As I'll mention later on, there's a certain amount of energy within the environment that you need to have. It's called the activation energy. So all of the reactants need to have a certain kinetic energy in order to collide with one another to produce the products. If you do not have the appropriate temperature, if you're below the appropriate temperature, then you just won't form products. Thirdly, is that you can increase the surface area of a reactant. So this one, you can think about how if you're doing a solution, as I mentioned earlier, if you increase an area, if you have, say you have like a cup of tea, right? And you can have either sugar as a powder or sugar cubes. If you crush the cubes down into powder, you can increase that surface area, and so you increase the exposure that the reactants have to one another to produce more product. And then finally, a presence of a catalyst. So a catalyst is a substance that when you place it into the reaction chamber, it lowers the activation energy. So it lowers the temperature that is needed for a reaction to occur, therefore helping speed up the reaction, putting in less effort, less energy than what is typically required. Okay, so collision theory, like I was talking about earlier, for a reaction to occur, you need to have reactant molecules collide to each other. And this is going to be described in a rate, which is going to be like collisions per second, or a number of moles of product produced per second or so. And then the methods to increase that rate I mentioned previously. So what kind of collisions are there? So not every collision is going to produce a product. Like I said earlier, you need to have a minimum activation energy is what it's called. So they need to have a certain amount of energy as they're colliding to each other for them to become products. And on top of that, the reactants also need to have the correct orientation. So if they bounce off each other and they don't hit at the right orientation, then they're just going to bounce off again. as we increase the temperature, we're going to increase all the kinetic energy within the system, therefore making the reactant particles move faster and faster. So we're increasing the number of collisions that occur, and as you increase the number of collisions that occur, you're also increasing the probability, the chances that one of those collisions will be in the correct orientation. And if you want to look to the side diagram to the right, you'll see from the reactants to the products, there's a transition state in between. So it's basically like a temporary state that the reactants are in. It's like almost kind of like a hybrid between reactants and products. But to reach that transition state, we need to overcome this activation energy. It's always going to be a little bit of a hump-looking shape, and then you can produce the products that you want. Okay, to measure the reaction progress, we've came up with a method to write out equations to figure out a rate. So looking at the example, so just having reactant A turning into reactant B, you want to measure the reaction by looking at the concentration of A, how it changes over the change in time. And we want to have a negative for our reactants because we are going to be losing reactants over time. And then looking at the second half, we have the change of the concentration of B, so our product, over delta T, change over time. And this will be positive because our products will be increasing over time. All right, it's all good. Thank you. Okay, so talking about stoichiometry and reaction rate. So this is the general formula that you'll see for any kind of reaction. So it's lowercase a, capital A. So the lowercase represents a coefficient, if there is a coefficient. If there's no coefficient, you should assume it's a coefficient of 1 written out. So products reactants A and B become products C and D. So the way you can describe the rate of the reaction is basically saying -1 over the coefficient of A times the change in concentration of A over the change in time. That describes the rate at which reactant A is depleting. And then you can set that also equal to, so all these rates that are written out will all be the same in the way that they're formulated. So this describes the rate of the reaction. Okay, so another way to relate the rate of the reaction to the concentrations of the reaction is using what's known as the rate law. So again, with our general equation here, A and B yields C and D. So we can set up a rate that says, so our rate, which is going to be the change in moles per second or some unit of time like that, is going to be equal to K, which is a rate constant, times the concentrations of each reactant to a certain power. So these powers, these exponents, X and Y, are going to have to be found experimentally. You'll typically, if they do ask you to find these exponents for X and Y, you'll be given a data table in which you'll have to compare different rates and different concentrations to see how to find that exponent. Okay. Oh, and before I move on, I forgot to mention that you can, so each of these exponents, the X and the Y, they are called in order. So if X is considered to be 1, in this case, just an example, if X is 1, you want to say the reaction is first order with respect to reactant A. If B has an exponent of 2, then you want to say the reaction is second order with respect to reactant B. And what we're typically going to deal with is going to be 0 order, first order, or second order. And then overall, the reaction, we're going to have a total order called the reaction order, and that's basically you just sum up each of the exponents. Okay, so this is going to be an example. I know you guys have just talked about this very briefly. You just are going over chapter 14 like this week is what I understand. But I'll show you guys an example of how to do experimental determination of the rate law. So you want to let's look at this equation right here. We have SO2 and O3 yields SO3 and O2. So to write out the rate law, you want to have rate equals K, which is the rate constant, times SO2, so the first reactant, to the X power, and then O3 to the Y power. And here is an example of a data table that they'll give us to compare. So you'll need, for however many reactants you have, you're going to need one more in terms of experiments. So since we had 2 reactants, we're going to need at least 3 experiments to help us figure this out. Okay, so running through how to do this. So as we're trying to figure out the rate law, just look at the table for now. I know the work is kind of overwhelming a little bit, so let's look at the table in the upper left for now. Whenever we look at a couple of the experiments, we want to see how changing the concentration just of one reactant will change the rate. So you want to choose 2 experiments to compare in which you're changing one reactant's concentration, but the other stays the same. So the other stays the same. And then you'll do it again for the other one. I appreciate all the comments on my handwriting. Thank you. So looking down at the lower left work, let's go ahead and compare 2 experiments. So it should be experiment 3 and experiment 2. I accidentally wrote 1, but it should be experiment 3 and 2. So if we're comparing a change in concentration for the reactant SO2, you want to have the reactant O3 to be constant. So experiment 3 and 2 will do that. So if you look at 3 and 2, our concentration of O3 is 0.2 and then also 0.2 versus our concentration of SO2 is 0.25 and 0.73. So like I wrote earlier, we have SO2 to the X component, and so that's what I'm keeping it as. So comparing 3 to 2, let's put 0.75 over 0.25 because it gives us like a whole number and we don't have to deal with any fractions. And then we set that equal to the rate of experiment 3 over the rate of experiment 2. Yes, I wrote 3 to 1 by accident. It should be 3 to 2. I want to make that clear. It should be experiment 3 and experiment 2. Okay, and then just do your division in your calculator. It should net you 3 to the X power is equal to 9. And so what is that? It's going to be X is equal to 2. So we have our exponent of SO2 to the second power. So that means that our reaction is going to be second order to the SO2 reactant. All right, so also having that in mind, look at your lower right-hand side. We're also going to do the same thing for the O3. It's known as ozone reactant. So let's compare experiment 1 and experiment 2. Looking at experiment 1 and 2, our concentration of SO2 remains the same. So we can safely ignore the SO2, and we're only looking at the change for O3. So again, O3 was to the power of y, and so we want to keep that formula the same there. So we're going to divide 0.2 over, or sorry, 0.4 by 0.2, because that'll give us like a positive number. And then we're going to divide the rates over each other. And since the rates are the same, we're going to have 1 on that right side over there, which is 2 to the power of y on the left side. And since we need to have an exponent of 0, any number to the exponent of 0 should net you a power of 1. I mean, sorry, a number of 1. So we'll have O3 to the 0 power. So we'll say that the reaction is going to be 0th order to O3. I saw a question talking about how do I know which. Hi guys, I'm not sure. I think I cut out for a bit. I'm not sure exactly where I cut out, so I'm going to backtrack a little bit about experiment, the second portion in the lower right-hand side. So again, we want to set up, we have O3 to the y power, and we're going to have set that equal to the initial rate. So we're going to choose 2 experiments. So since we're comparing O3, seeing what effect the concentration of O3 has on the rate, we're going to try to keep SO2 to be constant. So the only 2 experiments that SO2 is constant in, concentration of SO2, is going to be experiments 1 and experiments 2. So we have experiment 1 and 2. So in those experiments, O3 changes concentration from 0.4 to 0.2. So we can divide 0.4 divided by 0.2 to the y power. All that is within the y power. And then divide the rates by each other. And then since the rates are the same, you'll get a 1 on the rate side. And then when you divide the decimals, you'll get 2 to the power of y. And you'll need a 0. Y needs to be 0 for the equation to work, basically. So since our exponent is 0, we can say that the reaction is 0 order with respect to O3. Okay. And then one final thing I found in, oh, if you can go back real quick. Okay, so one final thing in the top right-hand corner, you want, when you write out your rate law, they ask you to write it out, you'll set rate equals K times the concentration of SO2. So to the second power, because we know it was 2, times concentration of O3 to the 0 power, because we found it was a 0 exponent. And if you guys remember, anything to the 0 power is basically just 1, and you can just ignore it. Say multiplying by 1 doesn't change anything. So our rate effectively is K, our rate constant, times SO2 to the second power. So for solving for the value of K, you just want to do some algebra, rearrange the equation. So you say K is equal to rate divided by the concentration of SO2 to the second power. And then you can choose any one of the experiments in the table. I just chose, I chose like the first experiment, and I plugged in the value. So I plugged in the rate value, and then we plugged in the SO2 value, and then I just did the math, and then I got my values. Okay. All right, so here I just want to give a little brief overview. I know this table looks a little daunting. I want you to have the main takeaway is looking at the left column and then the right column. So the left column tells you what reaction order, if you have that reaction order, and then the right column says what the units of K should be to correspond. So starting at reaction order of 0, you'll have molarity times, so M stands for molarity, times per second, so second to the -1. And as you increase your reaction order by 1, you're going to divide those units by molarity. So notice how it goes from molarity times per second to just per second to per molarity times per second to molarity to the -2 times per second. Okay? That was the main takeaway for that. All right, so now we're done with the review session. So we're gonna go ahead, and if you guys have time, stick around with us. We'll be breaking out into breakout rooms to do some practice problems. Let's take a look at, can everyone see? All right, everyone can see that.
Yes. Cool.
All right, so let's take a look at the first one. So first unit, thank you. We're gonna go over concentration units, so how to solve for molarity, molality, and then percent by mass, and also the trickier one, which is parts per million. At least it was for me. So the first one says a solution is made by dissolving 180 grams of glucose, which has a molar mass of 180.16 grams per mole, and basically enough water to make 1 liter. So we have 1 liter of the solution. Okay, so the density of the solution, we're told, is going to be 1.062 grams per milliliter. And then the question is asking us, what is the concentration of the solution in molality, percent by mass, and then parts per million? So I'm going to go ahead and do a whiteboard, write out everything that we have and what we're going to be looking for. Just 1 second. All right, so we're told here we have 180 grams of glucose. And that has a molar mass of yes. So I'm not sure if someone was saying in my chat, but I took down the problems because there wasn't enough space to write on it. So I'm gonna go ahead and just write out everything that was important. So it's a good way to practice. So whenever I do these kind of problems, the word problems can give you like a paragraph, and basically you only need like 3 different points or something like that. Oh, we're going to put mole there. We have 1 liter of the solution. Sorry, my pen is kind of laggy, so it doesn't keep up with me as I'm writing. So our density is what they told us of the solution is going to be 1.062. This is grams per milliliter. And so we're looking for a molality, right? So let's go ahead and change colors real quick. So molality. So do you guys remember what molality? What's the formula for molality? So feel free to type in the chat if you guys want to interact and all. Or yikes, it's lagging again.
Moles
yeah,
solute
moles
over
of
kilograms solute.
Right, thank you. Yeah, and just all the messages came in all at once. It's a little slow on my end. Okay, great. So let's look for our moles of solute. So let's basically 180. Oh, come on, 180 grams. And then we want to divide that by our molar mass, right? So it's basically 180.16 grams per 1 mole. Can anyone tell me exactly what that is? It should be a little less than 1. Let me see if I could. Okay, yeah, 0.999. Okay, thank you. 0.999. Okay. All right, so that's going to be our moles of our glucose. Come on. All right, and so we're going to need to put this all over kilograms of our solvent, right? So it's going to be important for us to figure out our kilograms of our solvent. So our solvent in this case is going to be water, but it's going to, let's see here. So we have 1 liter of solution, right? So how much mass do we have? So what we can do is use our density. What? Just an option. Oh, okay. Yeah, you're right. I always forget to use the text box. Let me go ahead and try using the text box sometimes. So basically, if we're using our density formula, let's see. So basically, let's go ahead and convert to milliliters, because our density was given to us in terms of milliliters. So what is 1,000, or 1 liter is going to be 1,000 milliliters, right? And then from there, we can do a little dimensional analysis, dealio. Right, using our density formula. So we know we have 1 milliliter, and then we also have 1.062 grams. So throwing that into our calculator, how much mass do we get?
Uh, 1062.
1062. All right, thank you. 1062 should be grams, and that's basically going to tell you that it's the same thing as 1.062 kilograms. All right, but this is kilograms of our solution, right? Solution. So basically, we need to find our kilograms of solvent. So how much, we need to subtract our kilograms of solute, basically. So we're told we have 180 grams of glucose. So what does that translate to? Translates to, let me put it right here, see this, 0.180 kilograms of solute. And if we subtract that, believe Justin's already figured it out for us. Yeah, you should get this many kilograms of solvent. So let's go ahead and write it out over here. 0.882 kilograms of our solvent. And then when you divide it, looks like he got, let me just write, sorry. He got 1.13 molality. All right, awesome. Did anyone have any questions over this one? Okay, so I'm going to go ahead and proceed on with the next part. If there are no questions, I'll go ahead and do the percent by mass portion. Okay, I'm going to clear the screen. Can we see the problem at all? Answer via chat, and then if we have problems, you can write out. Okay, give me 1 second. Now, let me see. Lucia's. She has a question on this problem. So where did you get the 0.18 kilograms of solute? Okay, so I was trying to do a subtraction problem over here. Okay. So we got the kilograms of solution, that makes sense. And then solute was glucose, remember? Over here, 180 grams of glucose. So we want to convert that to kilograms as well. So subtracting solute from solution, you'll get solvent. And that's where I got the 0.882 kilograms from. Okay, so could we see the problem, and I'll answer via chat. The problem you could write out on the blackboard. Oh, okay. Yeah, I guess I would speed things up for us. So I guess I can do that real quick. Let me go ahead and reshare this. Share application. Okay, so here's the problems again. So what we've had earlier was the answer would be, oh, here we go. B. Okay, and so for percent by mass, so I understand I'm being recorded to be uploaded onto the YouTube video. So I should try to at least give a explanation on how to do each portion of the problem. Okay, so molality we just did. So for percent by mass, what you want to do here, again, is you want to figure out the mass of our solute divided by the mass of our total solution, basically, and then multiply that by 100. So the mass of our solute was given, they gave us 180 grams of glucose, and they told us we had 1 liter of solution total. And they also gave us density, which was important. Density is going to be important to relate mass to volume, so to convert from mass to volume, basically. So using the density, you can convert 1 liter, which is 1,000 milliliters, to be, using the density, you get 1,000 and 62 grams. So you can either keep both the masses in grams over grams or kilograms over kilograms, as long as the units are the same. And then when you divide, you should get a percent, and then multiply it, or you should get a fraction. You multiply it by 100 to get percent. All right, let me just double check the key with what the answer is for this one. Yes, so for percent by mass, it should be B, which is 16.9%. Okay, and then the next one, parts per million. So to do parts per million, it's very similar to percent by mass. So you want to do the mass of your solute divided by the total mass of both the solute and the solvent. So the mass of the solution. But this time, instead of multiplying by 100, you want to multiply by 1 million, which is 10 to the 6th, basically. Or you can just type out the full 1 million. But either way, you want to, whenever you're doing that, you should get an answer of A up to the 5th. Yeah, so it should be A for parts per million. Did anyone have any questions over number 1? Any parts for number 1? Okay, so if not, I can go ahead and move on. And if you're watching from our YouTube video and you do have a question, feel free to drop in by peer tutoring to ask for help. And we always have a tutor on call. All right, so moving on to the second part, second question. Double check to see no one has said anything. Okay, so it looks like a student is given 75% alcohol by mass with a density of 0.79 grams per milliliter. And the student is asked to find the concentration. What should she report expressed in molarity and molality? And they give us the molar mass of isopropyl alcohol. Okay, so doing number 2. So since we aren't given exactly a percent, or it's actually a concrete amount of mass or molality or anything, we can just safely assume, let's say we just have 100 of everything, right? So they say that we have 75% by mass. So let's say that we have 75 grams of the isopropyl alcohol all over 100 grams total. Right, exactly, 100 grams total. Okay, so converting, we're asked for molarity, right? So molarity is going to be moles of your solute over liters of solvent, or sorry, liters of solution divided by liters of solution. So let's go ahead and convert 75 grams of isopropyl alcohol into moles. Okay, we should get a number. Should be divided by 60.1 grams. So let me double check. See what that is. Sure, should get 1.25 moles of your isopropyl alcohol. And then, So we have the top part of the fraction, which is our moles of our solute. Now we need to find our liters of solution. We were told that, where we said that we have 100 grams of our solution. And so let's go ahead and assume, not assume, we're going to use the density to convert from our mass to our volume, right? So if we have 100 grams of our solution and our density was told to be 0.79 grams per milliliter, so you want to divide that by 0.79. So 100 grams of our solution divided by a density of 0.79 grams per milliliter. And then for that, you should get 127 milliliters. Since our density was in milliliters or grams per milliliter, we're going to get milliliters. You want to convert that to liters. So that's going to be 0.127 liters, right? And I'm not sure if you guys saw, but Justin just figured it out for us. And so we're going to use our moles of alcohol, or moles of our solute, 1.25 moles of solute divided by our total volume of our solution, which we calculated to be 0.127 liters. And then we got 9.9 molarity. Okay, and yeah, our answer should be C for molarity for part 1 of question 2. Awesome, awesome. Okay, and so looking for molality, did anyone have any questions on how to figure out molarity? Okay, so moving on to molality. So the fraction for molality is going to be moles of solute again, divided by, this time, it's going to be kilograms of solvent. So since we already found our moles of solute, we just need to worry about finding kilograms of solvent. So our kilograms of solvent, let's look for that. So we have, so we're told we have 75% mass of isopropyl alcohol, right? So we have 75 grams of isopropyl alcohol over 100 grams of solution. So let's do 100 minus 75. So we'll get 25 grams of, we're going to assume that it's, this is solvent. We don't know exactly what it is. 25 grams of our solvent. So convert that to kilograms. So we have 0.025 kilograms of our solvent. Okay, and so let's go ahead and divide that. So we had 1.25 moles of our solute, which is again the isopropyl alcohol. And then you want to divide that by the number of kilograms of solvent that we just found, which is 0.025 kilograms. And looking here, it looks like that math will give us 50 molality, which should be answer A for the second part. Did anyone have any questions over how to get the molality? Okay. So let's move on to 3 real quick. So I'm going to scroll down. Okay. All right, so looking at 3, which of the following statements is false? So we're just going to go through each of them. So percent by mass is temperature independent. So you guys already figured it out. For 3, we'll still have to go through them. The first one for A, percent by mass is indeed temperature independent. If you look at the formula for percent by mass, it's going to be mass of the solute divided by mass of the solution times 100. And nowhere in there is volume involved. And so mass is temperature independent. So changing the temperature does not change the mass of a substance. So we're going to say that A is true. So molality, is molality temperature independent? We're going to say yes, because the formula of molality is going to be moles of solute divided by kilograms of solvent. And again, nowhere in that formula is volume involved. The next one, C, molarity is temperature independent. Okay, that's going to be true. Why are liquids temperature dependent, solids not? So it's not that liquids are solids, it's more mass versus volume. So as you heat up a solution, sometimes, or a solution, it can expand, basically, to take up more space, stuff like that, versus shrinking, like you're lowering the temperature, stuff tends to like shrink. Conversely, like water is kind of unique in that if you decrease the temperature, it'll like to expand. So it's not that liquids and solids, it's more mass versus volume. Okay. Mole fraction, so yeah, the answer is C. So that's going to be a false statement. So molarity is temperature dependent because it has, it depends on a volume in the denominator. And then just looking at D real quick, so mole fraction is temperature independent. Is that true or false? So mole fraction, basically you're saying it's a part over a whole. That's what fraction is. And so that means that we're going to have moles of a part, so moles of like your solute versus divided by moles of the total solution. So neither of those are a volume. They are like an amount, a quantity. So it's temperature independent. Okay, so if there are no questions on 3, we can move on. Okay, so looking at factors that affect solubility, which are going to be like temperature or pressure, let's look at question 1. So if you want to sweeten a cup of tea, it would be easiest to, if you stir the tea while stir the sugar while the tea is either hot, lukewarm, or cold. So this is like a real life application of the stuff that we're learning now. If any of you guys know, tea is typically served hot because of the very reason that you can stir things into the tea and it'll dissolve much faster than it would if it was cold. So if you increase the the temperature, basically, you're increasing the energy of the system, and all the molecules are going to move around faster, and they're going to mix much better, mix much faster. Versus cold, molecules will not want to interact as fast and all that. Okay, so looking at 2, Pressure significantly affects the solubility of which of the following substances? Yeah, so I'll let you guys have a quick read of that. So the answer in this one is going to be, it's a choice D, as in dog. So pressure typically is only going to affect gases, solubility of gases. So a really common example to think of is soda, basically. So our carbonated drink, which is like soda. As you increase the pressure, you're kind of like forcing gases like CO2 into the liquid. So that increases the solubility as you increase the pressure. Because gases are kind of just roaming around in the air, and by having pressure, you're forcing them into the liquid. So you increase the solubility. For solids and liquids, it's not as important because they don't really affect anything. Increasing extra pressure will not increase the solubility of a solid or a liquid, but it will do it for gases into liquids. Okay, so looking at question 3, what is the concentration of CO2 in sparkling water under partial pressure of 6 atmospheres CO2 at 25 degrees Celsius? The Henry's law constant for CO2 in water, 25 degrees. Hello, Visualities group. We're currently on question 3 of the practice packet under factors that affect solubility. So as I was trying to write out each of the questions earlier.
Oh yeah, I was just gonna say that's
Okay.
where we left off. So we're perfectly on the same.
Oh, awesome. That's perfect. Okay, yeah. So for what I'm doing with my group, I don't know, my tablet or my computer is like really slow for writing. So we probably would have been like a lot behind, but I'm currently trying to explain through everything, and it looks like most of my students understand the topic really well. So I'm just going to slow down to actually write out any problems that the students actually have trouble with. So otherwise, I'll just kind of like talk through with them with it. All right, so looking at question 3, yeah. Since we're told that we have a Henry's law constant, that's going to really highlight the fact that we want to use the Henry's law. So you guys remember Henry's law, which was concentration, so C is equal to K, which is the Henry's law constant, times the pressure of the solution. Okay, so since we're looking for concentration, we're going to need the Henry's law constant, and we're going to need the pressure. So basically, we're also given both of those. So looks like we're good to go. We have K, which is going to be 3.1 times 10 to the negative 2. And we also have pressure, which is 6 atmospheres. It's important that our units like balance each other out. So notice that our pressure is going to be in 6 atmospheres, and the units for Henry's law is also has atmospheres in it, so that the atmospheres will kind of cancel each other out if you multiply the units out. So looks like everyone is getting C as in Charlie. That'll be the answer. Did anyone want me to go and write out number 3 for you? Can you explain this? Okay, yeah. I'll go ahead and open up the whiteboard real quick. All right, so we're told that we have a Henry's law constant. So we're gonna think to use Henry's law. That's gonna point us in that direction. So Henry's law is our concentration, which we say was a big C, equals K, which is the Henry's rate constant, Henry's law constant, sorry, times P, which is the pressure of the solution. Okay, and so we were told that K was 3.1 times 10 to the negative 2. I believe it was moles per liter times atmospheres. And then we multiply all of that by 6 atmospheres. All right, so the atmosphere should cancel, and then you'll get a number divided, and the units will be moles per liter, so that'll be a molarity. All right, cool. Any other questions for this one? All right, I'll go ahead and reshare my screen. Can you guys see? Okay, here we go again. All right, so looking at 4, the solubility of CO2 in water is 0.034 moles per liter at 25 degrees Celsius and 1 atmosphere. What is its atmospheric conditions in which partial pressure of CO2 in air is 0.0003 atmospheres? Okay. All right, so what kind of equation do you guys think we ought to be using in this one? So for number 4, it's looking like we're trying to compare concentration and pressure, right? So concentration and pressure, those are going to be related by, Henry's law, basically. So we're going to use a version of like Henry's law. Let me go ahead and write this one out really quick for you, because I think it's a little more complex than the other ones. Okay, let me go ahead and share my whiteboard real quick. All right, I'm going to write things out in text box because that made it so much easier last time. So we're going to say K equals, right? So Henry's law is concentration equals K times P, and we can rewrite that to be K is equal to concentration divided by pressure. Now in this case, concentration is going to be C, let's call it 1, divided by P1. Little division sign. And we can set this equal to everyone is going to get a copy of the PDF after the session is over. So C2 all over P2. So we can say this is true because these guys will both be equal to Henry's law constant. So the law constant is a value of K, which is always going to be the same. It's a constant and won't change. So that's how we can set up this proportion. So having this out of the way, earlier we said that the first concentration was 0.034 moles per liter. And then we had a pressure, the related pressure was 1 atmospheres. Set that equal to and we're told our second conditions were 0.0030 atmospheres, and we're told for it's going to look for X, which is going to be moles per liter. All right, and it's a simple proportions problem. So you want to cross multiply and then solve for X, and then you'll get your concentration that corresponds to the second set of conditions. So I'll go ahead and share my screen again. All right. Hopefully y'all can see that. It should take a second. So number 4 should be A. A as an apple. Okay, and then next, moving on to colligative properties. So the first one asks, what is the vapor pressure of water over a solution made by dissolving 230 grams of glucose? And they give us a molar mass, and into 570 grams of water. They also gave us the molar mass of the solution, looks like. At 35 degrees Celsius. So they gave us also the pure pressure of water, which is 42.2 milligrams mercury. So what kind of equation do you guys want to use for this one? Okay, so since they gave us a pure pressure of water, that's gonna like hint you towards wanting to use Raoult's law. So that hints you towards wanting to use Raoult's law. You guys remember Raoult's law? Yes, so Raoult's law is going to be the pressure of the, what is it? The pressure of the solution basically is going to be equal to the mole fraction of whatever that the solvent is. So in this case, it's water times the pure pressure of, in this case, it would be water, of the solvent. So what is the vapor pressure? So we don't need to rearrange the equation in any way yet. So we have our pressure of our solution, sorry, vapor pressure of the solution is equal to the mole fraction of our solvent, in this case water, times the pure pressure of water. So they've already given us the pure pressure of water, so we want to figure out the mole fraction of water. So for the mole fraction of water, we want to do the mass of water divided by, or the moles of water, I'm sorry, divided by the total moles of the solution. So they told us here we have 570 grams of water, and we want to convert that to, okay, yeah, I can definitely do it on the whiteboard. No trouble. It's all part of the job. Okay, so we have 230. Okay, looks like he writes a lot faster now, which is good, or a little faster. Grams of glucose. And then we have 570 grams of water. Okay, 570 grams of water. Let me just write out the rest in the text box here because it's a little laggy again. So pressure of the water is equal to 42.2 millimeters of mercury. Awesome. So remember our equation for Raoult's law is that we have pressure of our solution, or vapor pressure, it's more appropriate, vapor pressure of the solution is going to be equal to the mole fraction of our solvent times the pure pressure, pure vapor pressure, to be better. Sorry, I don't think it's showing all up at once. Times pure vapor pressure of our solvent. Oh, that was a little messy. Let's see here. Vapor pressure of the solution equals the mole fraction, which is X, the solvent, times, let me write out another one, pure vapor pressure of our solvent. Okay, awesome. So they told us our pure vapor pressure of our solvent, which is water, which is 42.2 milligrams of mercury. So what we're really looking for here is a mole fraction of our solvent. So what is mole fraction, right? So mole fraction, again, is going to be It's called X, basically, but it's basically our moles of, let me write it out, I'm running out of space here. Moles of our solute, or whatever we're looking for, moles of a part divided by moles of the total. So in this case, since we're looking for the mole fraction of water, we want to do moles of water divided by moles total. Okay, so how do we find moles of water? So we have 570 grams of water. And then we want to divide that by the molar mass of water, which is 18 grams per mole. Grams per mole. So that should give you, let me see, 570 divided by 18. 31 point, let's say 31.7. We want to keep 3 safe things. Moles. H2O. Moles of water. Yeah, let's go ahead and say 37 or 31.7. Okay, and then what is the next one? All right, so we want to say moles total. Moles total. So to find moles total, we need to find the moles of our glucose first. I'm going to say moles glucose is going to equal to be 230 grams divided by, oh yikers, what did I put for? Let me double check the molar mass of glucose, which is 160. I'm sorry, 180.16 grams per mole. So that should net us 1.28, let's say, moles of glucose. Okay, so now we have our total. So let's go ahead and find our mole fraction now. So our total, say moles total, is going to be 31.7 plus 1.28. Should give us about, looks like if you round it, we got 33.0. I got 32.998, so that's going to be like 33 moles. Okay, so it does get moles of total. All right, so now we're looking for our mole fraction. It's going to be 31.7 moles divided by 33 moles, which is equal to 0.96. Right, so these guys won't have units. Mole fractions are not units. They're just fraction, unitless numbers. So we're going to say the pressure of our solution is going to be equal to 0.96 times 42.2 millimeters of mercury. So I got approximately 40.5 millimeters of mercury. So it should correspond with, looks like C for colligative property. Yeah, the answer should be C, which is 40.6. So just a little off, because probably I rounded differently than what they had done. All right. Did anyone have any questions? Okay. Is there a reason we multiply mole fraction by vapor pressure of water? Okay, so that's part of the Raoult's law. So Raoult's law is the mole fraction of your solvent times the pure vapor pressure of what you're looking for. Since we're looking for the vapor pressure of water in the solution. So we're going to look for the mole fraction of water, and we're going to look for the pure vapor pressure of the water. So that's why we multiply them together. So the vapor pressure of the solution should always be less than the pure vapor pressure, because adding in a solute will decrease it. So vapor pressure of the solution is only determined. Vapor pressure of the solution is only determined by a solvent. In this case, it's determined by a solvent. It really depends on what you're looking for. So in this case, we only had one volatile substance, and everything else was, or the glucose, the solute, is not volatile, so it will not produce a vapor pressure. So if you had a solute, like say you had another liquid that can also give vapor pressure, and you are asked to find the vapor pressure of that other liquid in the solution, then you want to get, let's say it was, what's another liquid? Let's say it was benzene. That's a liquid you guys will work with in OChem. So let's say you had benzene and water, and you're trying to look for the vapor pressure of benzene. So you want to find the mole fraction of benzene times the pure vapor pressure of benzene to give you the vapor pressure of benzene in this solution. So to find the vapor pressure of what you're looking for in the solution, you want to find the mole fraction of what it is you're looking for times the pure vapor pressure of what it is you are looking for. Pure vapor pressure of what it is you're interested in. Okay. Did anyone have any other questions? Okie doke. Go ahead and move on then to 2. Go ahead and share my screen again. All right. Should be loading for you guys. Okay. Cool. So let's looking at number 2. So it's asking us what is the freezing point and boiling point of a solution containing 690 grams of ethylene glycol, so they give us a molar mass, and 2,075 grams of water. And so we're also given a Kf and a Kb. So if we're given a Kf and a Kb, it's going to hint us towards wanting to use the change in temperature formula that we've known. So it's change in temperature, so delta T is going to be equal to K, which is the constant for either freezing or boiling, times the molality, times the Van Hoff factor. So what is the Van Hoff factor in this case for ethylene glycol? Yeah, so ethylene glycol, you guys will get better at this as you do more problems, but it's a non-electrolyte. It's a molecular compound. It's not ionic, is what is important. So it does not break apart into ions in solution. So its Van Hoff factor is going to be 1. So that means we don't need to worry about it. Then we have to figure out the molality. So if you guys remember, molality is going to be moles of your solute divided by kilograms of solvent. So we have here the mass of ethylene glycol. So you want to divide that by the molar mass of ethylene glycol to give you moles of your solute. And then you want to divide it by kilograms of your solvent, in this case, which is water. So convert that 2,075 grams of water to 2.05 kilograms of water. And then you'll get your molality. And then you multiply it by Kf or Kb, depending on whether or not you want to find the freezing point, which is Kf, or the boiling point, using Kb. So the answer for 2 should be D for the freezing point, and then A for the boiling point. Did anyone have any questions on this one? I'm more than happy to go ahead and do it for you if anyone had any questions. Nope. Okay. All right. Just feel free to stop me anytime. Like even if I've moved on to the next question, just leave a comment to go back and re-explain something, and I'm more than happy to do that. Okay, so let's move on to 3. So what is the osmotic? We'll see load. What is the osmotic pressure of a solution that contains 15 grams of butyl alcohol dissolved in water to make 610 milliliters of solution? Okay, so we're told here that we're looking for osmotic pressure, so that's only one formula that we can use, the osmotic pressure formula. All right. Okay, so the osmotic pressure formula, if you guys remember, is osmotic pressure is equal to the concentration of the solution times the gas constant R times the temperature in Kelvin. So for number 3, you want to convert the 25 degrees Celsius to 298.15. Is that correct? $298 or 25 plus 273.15. Yeah, 298.15 Kelvin. And then figure out the concentration of the solution. So in this case, concentration, we need to have it in moles per liter. So go ahead and convert the butyl alcohol into moles, and then using the molar mass that they've given you, and then divide it by the volume and convert the milliliters to liters, and then multiply it by the value of the gas constant. Let me double check which gas constant it is you guys use. Yeah, so the gas constant should be 0.0821. or 0.08206. Yeah, you should use that one to be more precise. Okay. Anyone want me to go ahead and write this out on the whiteboard? So it should be about 3 variables you're looking for that you need: the temperature in Kelvin, the concentration in molarity, and then finally was the ideal gas constant, which is again a constant. So that's just a number you need to memorize. I'm not sure if they'll have it on the exam for you. All right, if there's no questions on 3, we can move on to 4. Okay, so it says here that if 1 mole of each of the following substances is dissolved in 1 liter of water, which one is expected to depress the freezing point of the solution the most? Okay, so let's think about the formula for our freezing point depression. So delta TF is going to equal to KF times molality times the Van Hoff factor. Since we're told here that it's only 1 mole of everything, or of each of these fellas, we know the molality is going to be the same for all of them. So molality, remember, moles of solute divided by kilograms of solvent. In this case, 1 liter, 1 kilogram of water. So that means our molality will not be important because each of them will have the same molality. Similarly, the KF value, KF is going to correspond to the solvent, which is water, and each of them are in water. So KF can be ignored because they all have the same KF. So that leaves Van Hoff factor, which is I. I is going to be the deciding factor for each of these. So let's go ahead and check the Van Hoff factor for each of the question choices. So for A, we have NaCl, so Van Hoff factor should be 2 because we have 2 ions. So for B, we have a Van Hoff factor of 2 as well, so we have 2 ions, Mg and SO4 2 minus. And then for C, we have a Van Hoff factor of 3 because we have 3 ions, calcium 2 plus, chlorine 2 chlorines. For D, we have a Van Hoff factor of 1 because it is a non-electrolyte. It is not ionic. And then E is going to have a Van Hoff factor of 4 because you have an iron, chlorine, chlorine, chlorine. So it looks like E is going to be top dog. It's got 4 ions, so it's going to have the highest Van Hoff factor. It's going to depress the freezing point the lowest. It's going to change the temperature. All right, did anyone have any questions over this? Okay, I'll go ahead and move on to the chapter 14 stuff real quick. Okay. All right. So let's look at reaction progress. So looking at 1, it says to explain why the rate of disappearance of NO, nitric oxide, and the rate of formation of N2 darn, I forget the chemical name for N2, are not the same. So if you remember from how writing the reaction rate, basically it just comes down to looking at the coefficients. So looking at the coefficients, you know that NO has a coefficient of 2, and N2 has a coefficient of 1. So NO, the coefficient of 2, basically states that, hey, this guy is being consumed at 2 times the rate that N2 is being produced. So had it been 3, then it'd be like 3 times consumed at the rate then N2 is being produced. So imagine if N2 had a coefficient of 3, then NO would have a rate of 2/3. So it'd be 2/3 as fast. So the rates are going to be dependent on the coefficients within the equation. So just comparing what you are interested in this case it'd be NO and N2, looking at their coefficients, it's basically going to tell you why the rates are different and approximately, comparatively, how much faster or slower it is. Any questions on number 1? All right. Okay, so moving on to number 2. Number 2, so the USF formula. Yes, so NO is nitric oxide will disappear twice as fast as N2 because it has the coefficient of 2, basically. All right. So again, looking at 2, oxidation of ammonia. So that we have that long equation right there, and we're told that the rate of formation of N2 was 0.27 moles per liter. Okay, so let's go ahead and figure out the rate of the reaction, basically. So our rate of our reaction, right? Is going to be equal to, if you guys remember on my slides, I talked about you want to put 1 over your reaction, over your coefficient. So we're looking at N2, so 1/1/2 times, I believe it was 0.27. So let's see what we got here. So we should get -1 point. Oh, sorry, shouldn't be negative, should be positive. Sorry here. N2 here is a product, so this will be positive. 0.135 moles per liter per second. Okay, awesome. So now we're being asked what is the rate that water is being formed at. So if this is the rate of the reaction, this guy is going 2 times the rate of the reaction. Therefore, this portion is going 6 times the rate of the reaction. Oh, did someone have a question? Times 6, basically, you can get 0.81. It should be, let me double check that. Moles times that. Did you guys understand how I got that number, 0.81? Okay, so it looks like you guys understood. And then it's going to be very similar for the rate of ammonia being consumed. You're going to go ahead and do 0.135 times 4, and then you should get 0.54. All right, awesome. Okay, moving on to 3. So the manufacture of sulfuric acid is the reaction of SO2 and O2 to produce SO3. So we want to go ahead and write the expression of the reaction rate in terms of the rate of change of the reaction for each species. So it's very similar to what we were doing earlier on the last question. So to relate each of these species to the rate. So let's go ahead and do SO2, right? Since it has a coefficient of 2, we'll do -1/2 times change in SO2 all over change in T, which is also equal to negative delta 2 all over delta T. And again, it's just equal to positive 1/2 because this is a product. So 3 all over delta T. Oh, yeah, that's it. Okay. Anyone have any questions on 3? Okay. So let's go ahead and move on to the experimental determination of rate laws. Okay, so this is pretty new stuff. I'll go ahead and let you guys take a look. Okay, so looking at this one, let's write out our rate law. So a tentative rate law. So let's say rate is equal to K times W to the X power times X to the Y power. All right. That's so we're looking for the exponents basically. So let's try to figure out the exponent for W first. For W first. All right, so let's look at ones where we change the value for W and we change but we keep the value for X, the concentration for X the same. So it's looking like it's going to be experiment 1 and experiment 3 for me. So we have our experiment 3. Let's do 3 over 1 because the number is going to work out a little nicer. So basically we'll say 0.10 all over 0.05 to the X power is going to equal to 1 times 10 to the -3 all over 5 times 10 to the -4. And so from here we should get 0.1 divided by, okay, we should get 2 to the X, which is equal to, let me see what this is. Divided by 2 to the 2. All right, so that means that x has to be equal to 1. All right, so that means we can knock out guys right here. So let's figure out what the value of x is. So I'm going to do this in a different color. All right, so looking at x, let's see one where the w values are the same. So it looks like we're going to go to experiment 1 and 2. So let's go ahead and do experiment 2 all over experiment 1. So we're going to say 0.04 all over 0.01 to the y power. So then you'll get 2, I'm going to say times 10 negative 3 all over 5 times 10 to the negative 4. So this should be 4 to the y power. Should be equal to 4. Okay. Then you also get y equals 1. Okay, so that means it's going to be D. Oh, okay. Shadow Realm. Okay. So this is my work for, I'm not sure where I went to black screen, but what the work in blue is work for finding the exponent for W, and my work in red is finding the exponent for X. Okay. Did anyone have any questions on how to do this data table? Looks like we need to go take a look at 3 in the last page real quick. So I'm going to go ahead and scroll back to number 3 in the last page. All right, so looking at 3 from the last page, was there any specific question on number 3? Or was it just to look at the answer again? Okay, yeah. All right, cool, cool. So let's go ahead and move on. All right. Okay, looks like I'm getting some chat. Okay, so looking at number 2, we're going to have another experiment and another data table. And so it's asking us what is the rate law for this reaction. So let's go ahead and write out a tentative. Come on. Here we go. So we have rate is going to be equal to K E to the X power, and then F to the Y power. Okay, so looking at E, so let's look at one where our reactions stay the same. So it looks like F stays the same for experiments 3 and 2. So let's go ahead and take 3 and 2. 3 and 2. So let's go ahead and put experiment 2 over experiment 3. Okay, so it looks like we have 0.2 over 0.1 to the X power. And then we have rate is going to be 0.00064 all over 0.00016. That's a 1. So what should we get? We should get 2 to the X power is equal to, maybe that should be 4. Let me double check. All right, so we got all right, so we know that this is going to be wrong and this is going to be wrong. So let's go ahead and do the second half. Looking for the value, the exponent for F. So we need to find 2 experiments where E is constant. So it looks like we're going to lose 1 and 3. Experiment 1 over experiment 3. Whoa, what happened there? Okay, experiment 3. So you'll get 0.2 over 0.1 Y power, and then you'll get 0.00016 all over 0.00016. And from here, you'll get 2 to the Y is equal to 1. So you have Y equals 0. So that means that this will have to be the answer. Any questions on the first half here? All right. Yeah, it should be F. Okay, so now they're asking us to find the rate of the rate constant value, basically. So the way to do that, since we already know our rate, oh gosh, is K times E squared, we can say K is equal to rate times, or all over E squared. And then we just choose any value. So let's go ahead and choose just experiment 1, just because. So let's throw the rate on top there, 0.00016 all over 0.1 squared. So 0.00016 divided by 0.1 should get 0.016. All right, so we know it's either going to be A or C. So what are the units? Yeah, so it's going to be A, because if you take a look here, let me choose a different color. orange. So our overall order is 2, because we have that 2 there. Oh my gosh, drill over it. 2 there, so that means our overall order is going to be 2. So that means, if you guys remember from the table I listed earlier, this is the units that corresponds to that, which is per molarity per second. Okay, doke. Any questions on number 2? Okay. No questions on number 2. I can move on to 3. Last question. All right. So one more data table. So the initial rate data was taken from the following reaction. So it looks like we have a reaction with actual chemicals this time, not just letters. So H2O2 yields H2O and oxygen. Okay, so it looks like we only have one reactant. So we can go ahead and just write out the tentative rate law. So I'm going to say rate is going to be equal to K times H2O2. And it's X. Okay, this one's a little tricky actually. Looking back at it now, since we are missing, since we do only have one reactant, we'll have to find a way to see what changes. Or technically, I guess we have 2 reactions, but they are the same reactant. Rate equals. Sorry, I'm kind of like, it's a tad bit stumped here. Give me 1 second to think this out. Okay, it looks like G3 asked a question here. If one of the reactants didn't have a 0, can we go ahead and plug in the molarity of both reactants and solve? Yeah, so if the one of the reactants didn't have that order of 0, then you would need both of the reactants concentrations to do that. Choose any 2 equations really. We don't need, because there's no other reactant you want to need to worry about. Let's go ahead and choose experiment 3 and experiment 2, because I like their smaller numbers. The smaller your numbers, typically, the easier your numbers, the easier the problems will be. Anyways, let's do experiment. Let's say 2 all over experiment 1. Experiment 3. Experiment 3. So we'll say 0.02 all over 0.01 to the x power, and then we're going to say 2.4 times 10 to the negative 4 all over 6 times 10 to the negative 5. So we should get 2 to the x here should equal what number? Let's throw that into our calculators real quick. So we should get 4 on this side. So our x value here should be 2. All right, and so looking at, let's choose a different color. Let's choose red. Okay, so we're looking at our K value is what we're looking for. So again, K is going to be rate over our concentration that we figured out to be 2. So let's just choose any rate. So let's just choose the bottom experiment. It's right here. So we'll say 6 times 10 to the negative 5 all over 0.01 squared equals what? You should get 0.6. And what is the units? It's a second order, remember? So it should be to the negative 1 times to the negative 1. Okie doke. So this is us to the end of the review session. That's the end of the packet. Let me go ahead and read any of the questions in the chat. You get a different answer if you use 1 and 2. Oh, is that right? Okay. Let me go ahead and look at the problem here. 1 and 2. Okay. Let me see here. What's going on with 1 and 2? Let me choose a different color. Over experiment 1. Okay, so let's go ahead and do 2 over 1. All right, so experiment 2 over experiment 1. Let's double check. So 0.02, oops, 2 all over 0.05. Oof, that's not going to look pretty. Okay. Well, maybe it'll be fine actually. So let's call this y. So that's going to be equal to, looks like 2.4 e to the negative 4 divided by 1.5 e to the negative 3. So let's see what that gets us. 0.02 or 0.05. This should get us 0.4 to the y power, And then this other thing should get us 2.0002 divided by 0.005. So should get us 0.16. So y in this case should also be 2. Yeah, it should be 2 still either way. Yeah. Yeah, so I think it's been maybe a calculating error. Having trouble with that one. Yeah, that's how you should get. Questions on anything we discussed? It doesn't have to be practice exams. It can just be the topics in general. I'll stay behind just a little bit longer to answer any questions, but other than that, thank you very much for hanging around for the whole time with me and doing the review packet. All right. Otherwise, you guys have a great night. Good luck on your exam on Saturday. And I'll send out an announcement probably on Friday. But we're also going to have, it's just an advertisement for peer tutoring, but we will be having pop-up tutoring on Friday, all of Friday. We're open from 11 a.m. to 5 p.m. You can drop in at any time. We're going to have some extra tutors to help explain concepts if you're still struggling with anything, or just want more explanations, or if you need someone to look over your work on how to do stuff, we'll be here for you in peer tutoring.